am still an Elon fanboy. In fact, I think that one of the things Elon will be remembered for is he's one of the most quotable people in history. And I even have 100 of his quotes at the end of the book, The Elon Musk Mission. However, I've talked about,
I agree, Randy.
You agree
in this
what?
case, Elon is wrong.
He's wrong. So this is Randy Kirk. That's what we're going to talk about today. If you like having Scott on the channel, if you like having this kind of conversation, then hit the like button, hit subscribe, hit notify, and of course, same thing, go over and, hit Scott up. I mean, if you're not following Scott on Twitter, that's really not so smart. I don't know how much are you doing a lot of YouTube videos yet? Or are you still playing just on other?
I play YouTube Squatter. Yeah.
Squatter. Okay. Yeah. Squatter. Yeah. Okay. All right. Okay. Let's get into it. On the subject matter that Elon Musk is wrong about, and it is.
Well, let's say it's going to be about Optimus.
Yeah.
Surprisingly. Yeah, exactly. And so everyone's going,
right.
Whoa, what could he be wrong there? And I think it goes back that when I first saw Optimus come out in AI Day 1, that was like August 2021. I turned and quipped to a friend of mine. It's like, in this case, Elon's going to be wrong because the prototype will be hard, but the production will be easy.
There you go. So this brings up the whole issue. And I think that the Optimus is in fact the right way to talk about this, but just for a little more background, everybody knows, of course, I was a manufacturer for 30 years. I've brought hundreds of products to market. You've been helping manufacturers. Have you brought manufactured products to market as well, or just helped?
Not personally, but I've helped people simulate the processes to get them to there, to find out what all the issues are. And I've seen what the problems can be to get to production in a lot of things. Yes.
Right. So, I mean, everybody famously knows if they watch my channel, I did water bottles. Water bottle design and development was extremely difficult to get it to the point of where it didn't leak. For instance, every single bicycle water bottle before we started making them leaked. So one of our goals was to not have our bottles leak. And that took iteration after iteration after iteration, but it wasn't about the production. It was about the design. It was always about the design. And I think that's part of it, Scott. How would you define, what is the difference? Where does it become design? Where is it actually a prototype? Where does it go from prototype to first article? Or, I mean, I called things first article. They were talking about this yesterday with the model, with the new Model 3, and talking about how he was going to go see the first prototypes come off the line. I would have never called those prototypes. Those would be first articles. So how do we divide up these definitions?
Okay, well, before we do that, aloha, Randy.
Well, thank you. Yes.
Yeah, you were coming from?
I am in the beautiful state of Hawaii, in the island of Kauai, in the Princeville area. I can see the golf course from that window and the beautiful ocean and the sunrise every morning from my bedroom. This is not a bad place to be.
Okay, so I found the most Hawaiian shirt I could to celebrate the fact that you're out there. Yeah. So, what was the question again?
So where is something a prototype and where is it a production?
There's a transition.
In between,
the first thing you always want to come up with a proof of concept to make sure that you've got something that's going to work, that you're going on the right track. And of course, there's a lot of iterations to try to get that design right. And we know you can get it and it looks pretty good. And then you want to start scaling it up. And sometimes scaling it up can be very difficult. And that's what Elon is talking about, something, very complex, like an automobile. It's pretty easy to put together some sort of prototype in the shop. It looks very nice. You can bring it to a trade fair. Everyone is, oohing, eyeing over the whole thing. And now you got to figure out how can we produce it at scale and make sure it's affordable. And maybe some of this new weird tech we've kind of put in there. And especially if it's a process or something you haven't done before. So if you're just taking the same old models, making tweaks to it, you're just changing little things on the production line. But a lot of times it can be flipped around, that the design process is really hard, that, you're really trying to perfect it. So, we talk about the case that sometimes coming up with a plastic part that is going to do something really novel and interesting takes a long time to design that thing right. And to go through the iterations and to see that, when does it fail? and then these different use cases, and you find out, oh, it's not good in heat, it's not good when it's exposed to light, it doesn't like moisture, it doesn't like this or that, and then you finally keep on working it till you get that right. But once you have that thing right, you can knock it out very easy with injection molding. I mean, injection molding is, in many ways, it's easy as far as being able to set it up. It is an art. It's not to say that it's something that is not complex and there isn't a lot of ingenuity that has gone into it. Clearly has, but it's down to the point that you can come up with the part, you can produce it. So there are cases where the prototype can be very hard and the manufacturing will be easy, just because it's almost set up that way, right?
Yeah, well, in fact, I mean, I'm old enough to go back before 3D printing, practically before CAD CAM.
Yeah.
I'm not sure when CAD CAM really became a thing, but I've been in business since 1970. Anyway, back in the day, I mean, if you were going to create a product, if it was going to be a physical product, commonly you would make it out of clay or out of wood, or you'd have a machine shop that would, it was going to be better to make it out of some metal, but you were making a first sample. You're creating something, and so that you could use it in the real world and see if it actually worked before you went to even the stage of creating dies or tools or molds or whatever it was that you were going to use to manufacture the product. And of course, as time went by, it's so much easier. In fact, I did a YouTube video on this about 2 years ago. You can still probably find it on my channel. It's so much easier today because you can still, if you want to make it out of clay or out of some moldable, something that you can do moldable or cuttable or whatever, you can still do that. But a lot of times now you can send a drawing, a simple, odd drawing that nobody could tell what it is, and a good CAD CAM guy can put that thing into a 3D printer, and all of a sudden you've got a part. Now you can play with that, and with the CAD CAM in hand, now you can go to the injection molder, and typically that should be able to be a fairly easy process. I've had it one time when it wasn't, but generally that should be an easy process then to go right into production.
Yes, and you have a lot of companies, machine shops that are producing some product, but they realize their CNC machines are idle a lot, and they're trying to find some way to keep them in use. And that's when they come up with this sort of manufacturing as a service, that either they're in a collective or they just wait for someone to send a design and say, yeah, we can go ahead and start producing that for you. So that's very common. The ability to get a lot of parts produced, simple parts, in some ways is a lot easier than people think. And again, it's nailing a design. And, if we kind of circle back, I mean, it's really about Optimus. We're always talking about Optimus here. And the whole point of that is what's it going to be like to scale this up, and the issues that are going to run into trying to do Optimus. Now, we all can agree that if a humanoid robot was so easy, we'd already see them. There's no doubt about it. And a lot of people have been working this for a long, long time. And so why does Tesla suddenly think that they can do this when no one else has been, Boston Dynamics has been trying to do this for 30 years. I think it was like Asimo Honda was even longer than that. There's been many, many other projects trying to do this, yet we don't see them. So clearly it's a very hard problem. And how can they suddenly, in 2 years come up with something? Because the problem was never really being able to build the robot or the mechanics. The problem has always been the software, always the software. And so now Tesla, through FSD and through the FSD chip that they have, has realized that, wait a minute, there's an application that can solve it. And I'm sure it came from, again, a lot of these other discussion points you hear out there that, you don't need a humanoid robot to do that. You can just go in and automate that. You can go in, you can always automate the whole thing. And if it was like, well, if it was so easy to automate, why isn't it automated? So if you look at the automotive plant, you'll see there's a lot of parts that have been able to be automated and others that still can't be, because they're just very, very difficult. And cabling and flexible items have always been an issue. Other things where you need a certain amount of dexterity, you need to kind of crawl in. It's just easier to do it with human labor, and no one's been able to figure out how to do it. Now, I did like your T-shirt example and showing those processes.
This was a video. This is a video a day or so ago. You go back and look at it, and we showed the production, how you print T-shirts with an automated t-shirt printer.
Well, kind of semi-automated. I mean, see it's again, it's example that you've got a problem here and you realize we can automate certain parts of it, but there's still parts of it that we can't automate very easily. We still need the human labor. We need the humans to like to feed it or to pull the stuff out or do that or servicing and everything else. And you're always trying to figure out how much more automation can we do here, 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 and here. And if you look what's going on, there's a lot of steps there. But the way they get the steps to work is like one person was focused on one thing. If you have one person that had to do everything, they'd be very, very slow. So to get the speed is like you just worry about one thing. And you do that repetitively. Of course, that's like really, really boring. It's like all I'm doing is I'm grabbing a shirt and holding it like this. I'm just doing that. Nonstop. Once again, I knock over my Optimus here. So we're going back and forth and back and forth. And it would seem like that step is so easy. You could probably automate that step. Oh yeah, you're right. You could automate that little step. But now it's got to go to the next little step that the other guy was doing. And we do that and you start scaling it out. And the next thing you know, you get this huge footprint and you've got these machines that are kind of bulky and just not able to do it. So if it was so easy to automate, it would have been done already.
And in addition, and maybe the most important, is that most people think in terms of, making millions of something. Well, when you're printing a t-shirt, commonly you're only printing 100 or you're printing 200.
Right.
And next time it's not a t-shirt, it's a hoodie. And the next time it's a sweatshirt with no hood. And every one of those gets loaded differently and has to be handled differently at every step along the way. Yes. And different weights, different sizes, all those things matter. And so a robot that only has to be set up every time you want to change over and do 100, no, that's not working.
Difficult. It's difficult.
Optimus now can be trained to do every one of those and identify which one he's doing without having to be trained every single time to do something different.
Absolutely. And that's the idea of flexible automation, is it's very easy to change something. So, one example I always like using is a bottling line, in different stages, depending upon the volume that you have. If you have a high-speed bottling line, like if you go to any beverage manufacturer, you could just see that those bottles are flying off the line. It's just amazing how quickly they fill them and put everything on there. That is hard automation. But if you then go in there and somehow decide, well, we're going to change the design of the bottle, make it bigger or smaller, do something like that. So it's like, wow, I mean, we can't do it because it has to be within some constraints or our parameters now changing. So it's not that easy to change over. And so a bottling line is very good at doing bottling, but absolutely nothing else. And if you need that kind of flexibility, that's why human labor is so good, is because it's extremely flexible and it's really good at small volumes. And then you get these medium-sized volumes that it makes sense to get kind of the flexible automation where the robots come in. So if it's like less than 1 million a year, usually more about less than 500,000 a year, it makes sense to start doing it robotically. So the reason why automobiles are spot welded robotically is because of that volume. But I'm sure if you were cranking out huge numbers of cars or the same model every year, you might think, does it even make sense to make robots? Maybe we could have some kind of hard automation that would be even better and faster at being able to, yeah, but you just don't have the scale for that. So that's where it all depends. You need the flexibility. When you get small batches, you can't do it. And again, there's like these little tasks that seem like they would be really easy to automate, and they probably could be automated, but it would be so costly. At the end of the day, it's just not worth it. There's no return on investment. And again, it ends up probably taking up so much space, and the training and everything else is needed. It's like, not worth it. It's just easier to bring in labor. So now you come in with something that is flexible. Optimus is not designed to be super fast. Optimus is designed to be flexible and deployable. That's the other big difference. It's a deployable asset.
Right. So if we go back to the original, the real reason that we would even care about this right now is in terms of how many Optimi will be created in the short term, how many will be created in the long term. You and I have had this conversation before, but I think it's good to have it again in that context of, no, it isn't always true that the prototype is easy and the production is hard. Sometimes the prototyping is the most important and takes all the time, all the energy. And in the case of Optimus, we're talking about machine parts, molded parts, plastic parts, wire, motors, which are also metal and copper and whatnot. So we have all these things that are pretty much, I don't know, in general, I think you would agree with me, most of those things are pretty easy to produce at scale. without probably, I would say, generally speaking, I was thinking with a product that I was designing, and almost everything that we were doing was plastics. And they were a full range: extrusion blow, injection, printing, all these kinds of things. We usually thought in terms of 6 months from the day that we designed it to the day that we got what we called first out. And once you have a first out product, you look at it and you go, does this do all the things it's supposed to do? And now you can just start production. If it doesn't do what it's supposed to do on that first out, you go back and weld up something and cut it again, or you go back and make a new mold if you really screwed up. But generally speaking, if the first out works, you push the button and you're going at full speed day one.
Yes. Yeah. And we've done this calculation before. So if we want to figure out how much is Optimus actually going to cost, we can easily bracket it. The low end is you take Optimus and you melt it down and you look at how much everything is going to cost. And it's majority aluminum, and it's going to weigh somewhere around 55 kilograms. And you just do the calculation and it's going to be a couple $100. And there's going to be a couple of, quote, exotic materials in there, like, copper, and that might be the most expensive. It's not going to be made out of anything truly exotic. And the reason why I know that is because Malcolm said that during AI Day 2 presentation, is that we want to produce this at scale, which means we're not going to use any exotic components like titanium or carbon fiber. All right. So it's very clear it's designed to be mass producible. So they're designing it with that in mind, not using any exotic materials. And we can go down the list of what are the things that are the hardest to manufacture, that really require sophisticated technology that's the hardest. What do you think it is, Randy?
I would think it was the motors.
Well, I would think in some ways, to me, it's like I can make the motors in my basement. What I can't make is silicon semiconductors. Okay. So right. Obviously, so the brains.
Yes.
That is clearly something which is like a type of limiting factor. But it's really not, because Tesla is already having them being supplied probably about 4 million a year, because they need 2 of them, right? For each car. Right. And so they're already at a run rate of 2 million. So it might even be higher than that right now. So if they need to pull off, and remember, we only need 1 for Optimus, not 2. So if they want to pull off 10,000 or 100,000, that's not a big deal. The supply chain's already there. They just order a little bit more. It's coming from Samsung, which has a fab. We can agree that's complicated, but it's still not costly because they've already set it up. Right. They're already designed for that. What's the next thing that might be the most complicated? I guess the cameras, but that's, again, it's a type of semiconductor. They're mostly commercial grade. They're not going to be anything that sophisticated. Plenty of supply chains. They're fairly cheap. They're easy to get. I can't produce that in my basement, I know, but I can go out and I can buy it fairly easily. So that's not going to limit it. And we know the cost is going to be down. See, the next thing that might be the most sophisticated.
Oh, and if we go back to the camera, let's say we did want a piece of complexity. Let's say for some reason we wanted it to have a wider vision than the camera that we have a perfect camera, except we need a little wider vision. You just go to the maker in this case, because you're buying it from a maker anyway. You say, I needed a little wider vision, and that's not going to be a complex issue to solve.
And that's probably a lens. I mean, that's not the CCD that's going to be in there. That's just like changing the lens, the optics a little bit. So that's not a big deal to change. And then you have the batteries. And again, a battery is like, I might almost be able to make something in my basement. It won't be very good quality, but I know people can kind of make batteries in the lab, but you want to scale it up. But Tesla's already doing that. They're already producing the batteries. They get no problem. And like the number of batteries that they need, didn't we do the calculation? It's only maybe a couple thousand Model Ys for like 1 million. It's a small number. So it's not going to like impact the rest of the business, of the fact that they say, oh, we're going to take these batteries now. So that's the most sophisticated stuff. And then of course the motors. Yeah. But again, the motors, they're building in-house in a lab. It's not a big problem. Some CNC machines, stuff like that. And once you get it, you can scale up that mass production pretty easily. And then you get some castings, and castings go back to Greek and Roman times, maybe even before that. It's been around a long time. So I think we've got that mastered by now. And I don't see anything, or any components that are tough in there. So like the bracketing, and say you melt it down to a couple $100 of raw material. So that's the cheapest they could ever go. And then you go up to the high end, it's like, it's easier to build than a car. Okay. So what's a Model 3? What's it cost them? 25,000, 30,000 or something like that. which has way more parts, way more complexity, all these other steps that are going on. It's not going, you don't have a paint shop when it comes to Optimus, right? It's like motors are already putting motors in there. And as far as the way to be able to make sure something is, they're designing for manufacture because that's their philosophy. It's always designed for manufacture. And they design the servos in-house. We're the same group that designed the motors that are in the Plaid and everything else. And that same group was designing it to be manufactured. And we know that because we saw it, I think, in Investor Day, where they showed the video of like how we're coupling, the design of the thing with the manufacturing with this big feedback loop. I was just blown away. It's like, I've never seen that loop so tight together that they really are thinking the design on how we can make sure it's manufacturable and really drive the cost down. So, they're already doing that in Optimus. It's like, it's not just that we're coming up with these really cool motors, but we've got to make sure that we know we can manufacture them and manufacture them easy. So it's easy. Putting it together is easy. The hard thing is that you got that chip in the middle of the bot and it just needs the right weights.
Yeah. Now I might be a little bit prejudiced on this because I had a product one time, a brand new product that was more complex than I was used to playing with, and we outsourced the manufacturer, and it had a bunch of different plastic parts, and all these plastic parts had to fit together. So I was thinking that maybe the most complex part and the thing that would be the production hell possibility is you've got all these plastic parts and metal parts and wires and pulleys and all these kinds of things, and now they have to actually all fit together and then work and not break and not get twisted, not be able to work in all kinds of angles and as the bot is moving. So it seemed to me that could be the part where, as you're making the final version, you're making now you're injection molding, now your machine shop, you're doing them by the hundreds or the thousands, and you're bringing these in and you're trying to put all these things together. You might go, oh my gosh, this doesn't fit the way we thought it would when we injection molded. Do you see that as being a positive that could them up another 2 or 3 months?
That could always be a possibility that as the part comes out and gets refined, it doesn't quite snap together the way expected. But that's like an amateur mistake.
Well, there you go.
They're not amateurs. They're going to work it out, and I'm pretty sure that whatever is the parts they're producing are really based on what they have. And if there's any little change, it's they understand the reason why they decided to make. There could be something silly that right now they are producing the castings for the legs and everything, and they have a certain shape, and they might decide we want to reduce weight, so somehow we're going to make like the bones hollow like birds, so it'll be much lighter and still have the strength. And maybe something in there just affects some parameter or something like that, but they'll be able to do it and understand how to get the strength because they are simulating this. And I think this is something that Brian brought out. He says, like, the whole idea of using the crash software and designing Optimus. I'm like, I keep forgetting about that they did that. It's just intense that they've gone down to that level. And everything about this has nothing to do with hardware. It's always about software. It's always ever been about software when it comes to robotics in my entire career. That's what we've been trying to do, is make it easier for people to program the industrial robots, the ones that are out there right now, to be able to do that task without it taking so much time. And, we know Elon learned the hard way because a couple things happened in Model 3, that it was designed for manufacture, but it wasn't designed for automation.
Right.
And they didn't quite realize that there was a slight difference there. And so along the way, they, someone said, well, we should do more automation and stuff like that. That makes more sense. So they kind of pivoted over there, thinking they could bring the robots in there. And a lot of it was that maybe they didn't have enough experience there. And also the integrators that are doing it were probably overly optimistic and thinking that they could do these things, and they realize that, oh, it's a bad fit for this, it's a bad fit for that. So there's lots of things you begin to realize that, wire harnesses are very difficult to put together. Anything that's flexible becomes very difficult. And then a lot of the tooling design. And so Elon learned the hard way there, that how hard it was to automate these things. And I'm sure he was thinking in the back of the mind, how do we actually get the automation? He's beginning to realize that sometimes the human form factor is the only way to do it.
Right.
And then once the FSD chip kind of get to a certain level, it's like, oh, that's all it is. It's not a mechanical problem. It's a software problem. And the return on investment. And I think we've talked about this before, either in your channel or in others, that I believe the result of the Optimus project, when it's over, is going to make industrial robots better. Because we're going to program those robots the same way we program Optimus.
Sure.
Yes, absolutely, absolutely. So
Yeah.
Optimus is not going to replace them, because those specialty robots are better at doing those particular tasks, much better, much faster, with maybe better precision, and they're just designed for that.
Right.
But there's always these other tasks that are around there, in which the humans are constantly involved, and we want to make sure that there is some way to do it, and Optimus is actually one way to do it. Makes sense.
Right, I can see that. And so then, all right, so let's say for kidding around purposes, let's say that they have a robot today, when we saw a robot that was working, but let's just say that today is the day, and they decide, okay, every part, the software is still going to be developed, we're still going to train, we got neural nets all that still has to happen, and it's going to get better and better and better. But as far as the hardware is concerned, we're ready to go to production. I'm saying that it's 3 months before all the tooling. Some tooling might be done in a month.
Yep.
Some tooling might be done in 2 months. Some tooling might take 3 months. But the tooling, basically, there's nothing in that piece of equipment that I can find that would take longer than 3 months to tool.
I agree.
Okay.
There's probably nothing, and you might be faster than that. I know a lot of people will say that sometimes to get the dies that you need could take up to like 6 to 9 months, kind of a lead time.
But that's assuming that you're sending it out to somebody who you didn't
Yeah,
as fast as
You
possible.
Right. And if you're Tesla, you can do it a lot faster. And it turns out that there are other ways, because people are using more and more 3D printing to make that a lot faster, to be able
But
to
like injection molded dies have to be done in a certain order. So you can't speed it up 100%. You can't say, okay, just cut it really a lot faster, because you have to cut it and then harden it and then process it and then cut it some more. And then, so there's steps, and you're cutting out the cooling design, et cetera, et cetera. So there's steps. I think maybe I've had one made in 6 weeks. But again, injection molding, we usually thought it in terms of 3 months, from start to finish, first out product, ready to go, 3 months. So to me, I'm saying give it 3 months. Now then, if you've got every single part ready to go in 3 months, ready to mass produce in 3 months at scale, all you got to do is push the button on the wall, and the thing will start making them.
Start producing those components.
Now you got the assembly. So now you've already been doing this all along. You've been testing every part that you've made, that first out part. You've been trying it, making sure that it fits into the next one. So as you're going along, everything is working. Now you've got the last 2 parts, they all work. Theoretically, you could, on day 100, you might be ready to start building this, but let's give them 3 months.
Let's
give them 3 months. Give another 3 months to build them, put them into a line of some kind, or an unboxed environment or whatever it's going to be, and start figuring out what the best way is to assemble these so that they can mass produce and really get up to scale. So that would be 6 months. So by the end of the year, if they were ready to go today in terms of the design, I'm saying that I can't, and I've built a lot of products. I mean, I really have. I can't see how they couldn't be ready to go with this on January 1 and just push the button and be making 100,000 a month.
Yeah.
I mean, when I was making bottles, you push the button, I was making 5 million a year.
Yeah, it would go quick. And I think they've already got the design on how they want the manufacturing line to look. And the reason I say that is because that seems to be the way they work.
Yeah.
They built Giga Shanghai so quickly, and they got the stuff in there so quickly. It's like they didn't do that on the fly. They had a plan. And so I think they put together the plan pretty quick. They knew exactly what they had to fill it with. They knew exactly what the layout was going to look like. They knew what they had to get up. And that is a lot of planning.
Yeah.
And that's so they're already thinking these things through. And I'm sure they've done the same thing that with Optimus. It's not like, well, when we get around to it, they've already got a department in there that's thinking it through and thinking how much floor space they need, what it's going to be set up like, what procedures they want to do to make it really quickly, so they can just snap these things together really quick. So it's not going to be some pilot line that they're just tinkering around with just to get an idea. I mean, they may already have like gone through a couple of pilot programs already just to see what's it involved, what's going on, so they can refine it. So like you say, when they're ready to say, yeah, the design is ready to go, they're ready to go. And it's really just coming down to software now. They get that software, it starts going pretty quickly.
Yeah, and I think you and I may have done a video on this also. I know that I either did it with you or I did it by myself. I think the other part that needs to be put in place, and maybe the limiting factor in 2024, is the training and social interface of Tesla with the customer, whoever the customer is, even if it's only Tesla. So I've got a guy who's in the Optimus training division, whose job it is to go with Optimus to the location and help integrate him into the Optimus, him or her, help bring Optimus to the floor, get the training done so that the people that are working with him all around the Optimus, they all know what to do, what to avoid, what not to do, et cetera, et cetera. And the Optimus gets used to working in that environment and is learning how to be in that spot and do the job.
Right.
I see that as being the limiting factor on how quickly they can be deployed. But I'm thinking it's maybe, I don't know, I think this is where the guessing really gets hard. I'm thinking that's a 2-day job for an employee.
It may be, I'm not sure what it is, but I referred to that in the past as like the absorption rate. How, you know, if suddenly they had 1 million Optimi tomorrow and nobody knows how to use it, you just can't absorb it. So you've got to maybe find the applications and you've got to find the people that know how to deploy it and set it up and get it going. So that takes a little while to go through there, but they'll probably be able to do that almost in parallel with production. Because again, they can't produce 1 million overnight. They're going to have some sort of ramp up and run rate where they're producing them at a sufficient rate that you can start getting teams going in and understanding, and they start to get the feedback and maybe think, oh, we're going to have to tweak a few things here and there. But again, it's going to be like FSD. It's just going to keep getting better every day.
Right.
Now, if they think that they really have the mechanics down with what they need, then it's ready to go. So is that hand got the dexterity that they need that will improve over time once the software starts going in and figures out how to do things a little bit better, you know, the control system for the balance. So it's suddenly, it's a little slow in walking right now, but it's going to get faster and faster just because of software, not because of any mechanical limitations or anything else they have to change. So I would see that happening over time. They seem to have enough in there.
Yeah, so I was thinking the customer service team, though, would be somebody who would be being trained as the Optimus are being trained now.
Yes.
So
yes.
there might be 10 or 20 or 30 of those people now that are learning how to train an Optimus. They may be sitting in the labs with the scientists and doing this, or they might be in a separate, you've talked about the building over there in Fremont that we've speculated might be for this purpose, but you might have 10 or 20 or 30 employees now that are learning how to train Optimus, how to train them to socialize them, to put them in the spot. And then those 10, 20, or 30 can now train 100 people. You know,
yes.
to be
So you're going to get the train the trainer situation,
train
right?
the trainer situation. So now you might have 100 or 150 people, and if it only takes, let's give it 3 days. Let's say it takes 3 days in a brand new situation, takes 3 days to train it. So one employee should be able to train 10 a month, not 10 a month. Would that be 10? I'm sorry. How could I not do that math? So in 20 days, if you can do everything, 7 a month. So he should be able to train 7 a month. So 100 employees could do 700 a month. And that would be 84,000 a year. So my million a year, you need another layer.
Right.
Those 100
right.
people train
and I know it's like, Yeah, there's a big difference between can they produce 1 million and
Yes.
once they figure out how to get the production line, the question is it going to be one production line or multiple production lines somewhere else that
Right.
they're just able to duplicate? And they could probably scale up to 1 million pretty quickly if, again, they have the the use case and some way to absorb that many. So you don't want to overproduce. And it's like, well, we don't have enough use cases for it, especially if they decide we want to keep it internal for now and not necessarily release it out to the world. But there may be that there's enough people outside that are clamoring that say, yeah, I got ideas. Like you were talking about the t-shirt factory there. And as you can see, it's all about not having one worker who's really good, but having enough workers that are doing a dedicated task together. So you're like, oh, I need 10 Optimi and I can run that thing. And they just go something very, very simple. But having one makes no sense because maybe one Optimus is just not fast enough to do that. But you put the two together, it's all right. Again, the Shanghai video where we saw the operator that was loading in 2 stations. So the human is fast enough to do that. However, it's also something that 2 Optimi, you could do it if they're not fast enough.
Yes.
So it's easy enough to do that. And I would think eventually 1 Optimi would be able to do both those tasks within the cycle time.
Yeah, in fact, in the t-shirt example, again, people can go back and look at the t-shirt video, the t-shirt example. In using that particular piece of equipment, you typically would only have one person that would be taking it off the dryer and putting it over on a table. You wouldn't have 2. They had 6. They had 2 people taking it off the dryer, handing it to 2 other people on each side. So you had 3 people in order to manage the speed of which that was being. But that machine typically would not be operating at that level.
And they were going for a world record there or something like that, right? Yeah.
Yeah.
So that makes sense. That the reason why you have to have the division of labor to make everything going there.
Right.
So it doesn't mean that the Optimus is so stupid it can only do one thing.
Right.
It can do multiple things, but there may be situations like you say is that if you want to get the speed, it may be that you really keep it dedicated so you don't have the transition to another task. You just keep doing that task and you do it very, very quickly and the other one does it. And that's the beauty and the reason why it has legs is because it makes it deployable. Yeah. So you can move it to where you need it to be. And, one story I can relate is that was an aerospace company back in like 2010 around there that came in and wanted us to do some simulation of the robots. And I was shocked when I went in there to find out that the robot they were working with was like the second robot they had within the company. And this is a big name. Okay, this is a name that you would know of, and I got that robot just because it's another group that's trying to figure out what to do with it. So they realized that they needed to bring more of that in. It's like, well, you guys are high tech, you're producing all this stuff. How did you get by without robot? You clearly have CNC machines and other kinds of forms of automation in there, but really no robotics. And it's like, well, it's because our volumes are so small. They might be producing kind of like one a day. And the result is that the operation that the robot was doing, it's over in 20 minutes.
Yeah.
And it's like, what's the robot doing the rest of the day? It's nothing because those robots are bolted down and they can't get. So they were like seriously looking at, okay, how do we put these robots on a mobile platform? The standard industrial robots, so we can move them around to somewhere else. So in the morning, it's doing this task and then it's doing another task and doing nothing else. And have to have some change of arm tooling because they needed to come up with a return on investment for having these things because they were not deployable. And that's the thing about Optimus is like, hey, we got a problem over here. Send them on over. They go ahead, take care of the problem. Oh, we got another problem over here, and then redeploy them. So that's why you want the mobility.
Yeah. So let's address one of the questions that came up. And in my videos, like any videos that are out there, people comment. We love your comments. I'd love to hear your comments, and I try to respond to as many as I can. And one of the comments was, gee whiz, we have not been able to automate the picking up of a t-shirt and placing it over in some other place because the pinchers or whatever, there's no way to grab onto them appropriately. And I just immediately, my brain went to you and I thought, I'll bet you I bet we could brainstorm on several ways that Optimus, as he's currently configured, can pick up that t-shirt because he has vision and he's being trained. He has a neural net. He has a brain, a kind of brain. So I had a couple of ideas. Go ahead. Did you have any ideas of how the picking up the garment um, which is a floppy, flexible, soft material.
I mean, the first thing is the fingers is understanding whether it has grasped something correctly or what it needs to do. And whether it has enough of the kind of the proprioception that you would need to be able to tell whether that's the feel that I need to have for being able to pick up one t-shirt. Because sometimes you go down and you go, oh, wait, I've grabbed 5. I don't need 5.
Right?
What's that feel that I know? It's like, oh, I got the 1. And I don't have the whole t-shirt. I just got like the top part. So when I lift it up, it kind of opens itself up. And those are the things that you might get from obviously looking at it and some sort of delicate feedback that you would just train it again and again to learn that. So again, I think it just comes down to software. It's not necessarily that we need to have some really fancy kind of end-of-arm tooling for it or think differently. Maybe there's a slightly different grip that you put on there. Like, if you look at workers, a lot of times, why do they wear gloves?
Yeah. Is
that some sort of cheat? It's because it gives them just the friction and everything else they need for that particular task. It also protects them a little bit, but sometimes it's exactly what you need for that particular task. So it'll be the same thing. You just got to put on some sort of fingertips, like you did.
Yeah.
Remember, sewing and stuff like that. You had a thimble for a reason.
Yeah, exactly.
So there's always going to be these little things that'll make it a little bit easier. And the bank teller, I remember the bank teller when they're counting the bills.
Yeah.
They always had a little special thing on their fingertips to be able to go through really quickly. So, so you'll have things like that, and you'll get the feel. You'll be able to see what's going on, and I'm sure all those tasks can be done.
Yeah, I was thinking
I didn't see anything that was hard at first. When I listened to it, I had to, I was driving home and I was listening. It's like, oh, Randy's absolutely crazy. And he's like, I'm a man. He's like, I bet that's really hard. Then I watched the video. Oh, there is nothing difficult going on there. When I actually visually saw what they were doing, I was like, yeah, it should be able to do it.
Yeah. No, I spent a couple of hours trying to find the perfect video for that particular production. I happen to have had a client recently that was that's the business they're in. They use the machine almost identical to that. So I've been out there watching that machine and watching humans doing those jobs a ton, trying to speed it up and make it more effective. And I think the loading is the hardest part. And the loading, I think even Optimus could do the loading. The loading, that guy was really good. He wasn't paying any attention to wrinkles. He wasn't paying any attention to exact location because he was just really, really good at his craft. But typically the guy who's loading, the thing he's paying attention to is, do I have that thing on straight? Do I have it on far enough and not too far? And is there any wrinkles? Because those 3 things can really mess up the print job. So you have, the Optimus should be able to see all 3 of those issues, and in terms of where it's located and also whether there's wrinkles.
Right. So what the operator was doing is that he wasn't thinking about how to take the wrinkles out. He was thinking about how to load it wrinkle free.
Yes.
That's the difference.
Yes.
So it's like, yeah, you can kind of put in your foot, all these wrinkles. Now I got to get them out. It's like, no, if you learn the right technique, you just like put it in there and guess what? There's no wrinkles.
Right.
So you do it right the first time. And that's probably something Optimus would, realize that what you have to do is make sure there's no wrinkles on it, and they're just going to keep on trying. And eventually, oh, this is the way I put it on in there. And then I will notice occasionally there's a little thing and it's just like a little pat and I'm done. As opposed to, I got to go through and stretch it. Because sometimes the more you fuss with it, the worse it gets. You may as well pull the thing off and start over again.
And again, what people also seem to, it's really hard even for me to get it in my head. Once you've trained one Optimus to load t-shirts on a platen like that platen, all of them now have that skill. Every Optimus now has that skill. So when you buy your Optimus and you bring it in, it's already more skilled than probably your most skilled professional at doing that. So that's
exactly.
That's it.
Exactly. My Tesla can do Chuck's left turn.
Yeah, I sure can.
I haven't been there yet, and I've never, attempted to do it, but my Tesla can do it because, they all know how to do it. So it's going to be the same thing. Yeah. Once it's been trained, they all can do it.
So the other question that keeps coming up, and I think we've answered this before, but I think we should answer it again, and that is the different modalities for training. So my understanding would be that the one possible modality is actually literally telling whether you're saying it out loud and the computer and the Optimus understands it, or whether you're typing it as a text correspondence to the robot and telling the robot what you want it to do: go higher, go lower, go left, go right. harder, softer, whatever. That would be one method.
Mhm.
Okay. Number
I
two method.
think the main method is going to be basically show,
So then you have the show, which is how we normally
which is
train.
basically the
Points.
demonstrate. Yes.
Right.
And I guess part of the reason is like, a picture's worth 1,000 words.
Right. Right.
So rather than trying to give the description and then it can be vague, it's subject to interpretation.
Right.
Just show it what you want to do.
Right.
And then after it's seen it, you then kind of label it, or you tell it that this is what we call that. So you know what it is in the future. I want you to do this and that. And then, it starts to associate it. But the main thing is it sort of sees those steps, understands what it is. And then you can say, okay, now I want you to do this over there.
Mhm.
And then you can say, oh, but make this slight modification. You might be able to tell it. But I think the most important thing is the task has to be shown again and again and again, it watching you and then it doing it. And then you may be saying, oh, that's wrong. This is how you do it.
And then is there a layer of complexity that where you would switch from a show version to wiring yourself up and putting cameras on your head?
There may, I imagine there may be where, if you're trying to coach someone to do something very, very difficult, a lot of times you might be describing first to them what's going on and then showing them and hoping they do it. And they're making lots of mistakes and you're trying to tell them, oh, you got to work on this, you got to work on that. And then you're doing other things to kind of hold them in place. It's like, oh, this is what it's going to feel like to do this particular flip. But other times you almost wish you could just get inside of them and tell them, this is how you do it. And so it may be that there's certain skills that are just so hard to describe, or you're showing it, but it's just not getting it. You might say, okay, we really have to go in there and show it some sort of nuance of what's going on for it to be able to understand that. But that I'm not sure how often that would be. What it might be is more like for a remote thing. Is we want to Optimus do something different now, but I'm not down on the floor.
Yeah.
I'm not there to show it.
Yeah.
So it's like, oh, let's just kind of suit it up and just say, take over, and that's what you're going to do.
Right. And then what about the simulation level? So that would be the most, I guess, sophisticated level would be you would create some kind of a computer simulation, which could be fed into the learning system.
Yeah. So there's definitely going to be a lot of simulation to help reinforce the training and to show different variations of what's going on. So it's one thing to say there's certain kind of tasks and this is how that task works, but now we need to make sure it understands that that part won't always be right there. It's going to be somewhere else. And we wanted to understand and kind of figure out how to take that and transpose it over to a different position and understand what that means with the body, is get that sort of sense. And we certainly know how to do that. I mean, we do kind of prefer to write with the piece of paper right in front of us. That's our preference. We learn that. But if you put it off on the side and you really want me to write my signature over there, I can do it. And I just, even though I've never done that before, it's something I know I can figure out pretty quickly and do. And that would be the same thing with Optimus, is that you're going to be teaching these things, but you want to make sure it's able to understand when it is in different locations and things are a little bit mixed up. Is it able to come up with a scheme to be able to solve that problem? And it should be able to.
Yeah. So then would you use these methodologies of feeding back in? You've got this set of knowledge, and feed it back on itself and build up a bunch of different edge cases and variations and versions. Yes,
because a lot of times it's going to be sort of different senses or feelings that have to come together that determine different things. So I've got a certain muscle memory that's going to be what my wrist does when I write. So it's all about my wrist. It's not about my shoulder or my elbow or anything else. But the positioning of my wrist is like a different sensation or feeling. What I want to be able to do is like take those different concepts and be able to apply them wherever it has to happen. And that one of them should not impact the other, yet they need to be able to blend together nicely, that I can go ahead and apply that kind of action there. So, certainly what's going on with your fingertips is very important for grabbing something, that sensation of picking up a piece of paper. But I don't want you to have the sensation of what it's like to pick up a piece of paper right in front of you. I want you to have that sensation of what it's like to pick up a piece of paper anywhere in your workspace. Right. And then you need to have the sensation of what it's like to position your hand anywhere that you need to get. And then sometimes the position of your hand is not that it's like this way or that way, but to understand what it is and then pull those kind of sensations in. And that's what the neural net is going to be doing. Is it's not, I know how to do that in simulation. I know how to run the math and the calculus and everything you need to be able to do things like that, but that's not how Optimus is going to do it. It's a pure neural net. So it's not trying to do those calculations. It's trying to say, all right, mentally, I know you want to put your hand in some location under the desk over here where you don't see anything. And I can tell exactly how to get there. And I'm not doing any trigonometry. I just know how to do that. And
Right.
then Optimus is going to have that same innate sense of how to go in there. And we have a pretty good idea with approach perception. You know, I do this all the time, close my eyes and, turn my head wherever, and I can still touch my nose.
Right.
I don't necessarily need my eyes to do that because I'm so good at knowing and understanding where all my body parts are.
Right.
And good enough that I could even take this and get a mental picture in my head of the bottle and look at that. You see, I'm able to get the end of the bottle and still figure out how to touch my nose, even without that being part of my body. But when I grab this thing, it becomes like an extension of my body. And we do the same thing when we drive. I mean, we feel the road, don't we?
Yes.
I mean, we get the sense that, those tires are almost like part of us. And these are one of the things that you would want to have going on in there. And the only reason that we have, our eyeball is that, I can kind of get the bottle right there. But if I want a certain edge on there, maybe it's a little bit tricky. And it's a good idea if I get my eyes to say, oh, I want that part to touch my nose or somewhere on my finger or something like that. So now you get that feedback that this gets you very close, and your eyes is what allows you to tune it in. That's what Optimus is going to be doing. It's going to sort of see the object. It's going to make a reasonable guess on how to get there just because it kind of knows. And then as it starts to go over there, it's going to do the mid-course corrections to go on in there and get it. And I know a little bit on how we sort of do that mathematically, but the thing about math is that it's this hack that is a very convenient way of describing what's going on in the universe, but I don't necessarily know that it is the description of the universe.
Right.
It seems to be
an argument.
It's very convenient. It does a very good job of being able to predict things, but I don't know that the universe is necessarily based on math.
Right.
It seems to be based on something else that we are seeing going on with the robots, and that we know how to do these things without applying high-level calculus. I mean, think about it, we've been throwing balls and catching balls for thousands of years, way before Isaac Newton was born.
That's right.
We didn't need calculus to be able to figure out how to chase a ball or to, throw a spear or shoot an arrow to hit a particular target. We just sort of figured that out from enough trial and error. And then suddenly something got programmed in us that we understood what that was. And that's the same thing that's going on in the neural net, is like you get enough of that. And again, it's like, yeah, you do need a lot of practice and repetition for our neural networks, but still, you get enough practice with a bow and arrow, and then you have to set up a shot you've never done before. You can make a pretty good guess and still hit it.
Yeah.
And the same thing with throwing a ball and everything else. It's like, pretty soon, or chasing down a ball is like, you've never had that ball hit to you exactly that way, yet somehow you were able to figure out how to get that thing. And part of it is you come up with a really good guess at where it's going to be. And then as you get there, you fine tune your way to make sure, okay, I'm able to bring it in. And that's what's going on. That's why the cameras are so important to Optimus. And they're so important to a robotic system, because the robotic systems don't have it, but they do have this ability to supposedly faithfully go to the same point again and again and again, because the mechanics are so stiff and everything else is programmed that way. And that we have these encoders, which are basically protractors on all your joints, to say exactly what the angles have to be. And some guy has written this math routine to say, if the joint angles are exactly this, I'll hit that Cartesian target exactly where it needs to be, and I'll hit that every single time. That's not the way the human body works. We don't have, our human body is like mechanically horrible compared to what an industrial robot is, yet we have more precision than an industrial robot. And why do we have that? Because of our brains. And one of my professors at Cornell, he nailed it on the head, like back in the 80s. I remember talking to him about that. And I thought he was a little bit crazy. He was like working on a project, this thing that he wanted to look at, like flexible robot arms, because he thought that the approach was completely wrong. So this was Francis Moon. And he because they were trying to make robots more accurate by making them stiffer and stiffer, and making sure you didn't have flexibility in the arms and all that. And that's one way to solve the problem, to get precision. But his feeling is like, well, wait a minute, first principles, we're pretty darn accurate with what we got, and like, look at what we're made of. We're not made out of steel and with these high precision encoders and everything else, and those guys. Somehow we're able to get this great precision, and a lot of that he already knew it's because of the feedback and sort of understanding a little bit about the flexibility of our bodies and be able to react and respond to that. So that's pretty much what Optimus has now done. So that's his concept. That's what he's thinking of how it's done. That was a software problem. And he was right. Professor Moon, you're out there. You were right. That's the way to solve it.
So what we've done today is we've taken a look at the Optimus, and we've asked the question, is prototyping hard or is production hard? And we're modifying Elon Musk's very famous quote. It's been repeated and repeated and repeated. We're modifying it to say automotive prototyping is simple compared to automotive production.
Right.
That doesn't mean that applies to every single part or every single product that is manufactured. And in the case of the Optimus robot, Scott and I are agreeing that the Optimus prototyping might have been difficult. The neural network part of it certainly is difficult, but doable. But the hardware aspect of it is not that hard, shouldn't be that hard to get into production. My number of 1 million in 2024 might be crazy off the charts, but I don't think it's because of the inability to produce 1 million good ones next year. I think we could produce 1 million good ones next year. It may be the deployment, the socialization, the customer service staff that would be necessary to go out and help manufacturers put it into action, actually have it start doing useful things. That might be a reason that would make it more difficult. But again, that's really just a multiplication problem too. You just need, how many trainers do you need to train the new trainees? And you can multiply that really, really rapidly, I would think. Maybe I'm wrong, but that's what I think. At the end of the day, it doesn't really matter whether they deploy 500 this year in their own factories or 1,000. Scott's around 500, I'm around 1,000. It doesn't matter whether they deploy 250,000 only in their own buildings and in the buildings of their suppliers next year, or whether they deploy 1 million next year and those 1 million go out to all kinds of new customers that they bring online. What matters is the progress, and that ultimately at some point we're going to be making 10 million or 20 million a year of these robots and changing everything.
Yes. A lot of things are going to change.
That's what really matters. So Scott, always fantastic to have you on board, because my brain only goes, see, you're in the screen right there, you're taller than me. It's because your brain is taller.
Maybe, I don't know.
So anyway, for those of you in the audience, if you like this kind of stuff and you want Scott back, hit the like. I know you'll do that. And then if you want to subscribe and hit notify, that'll help you see, because I got a whole bunch of other guys that are almost as smart as Scott coming on the next couple of days. And then of course, go over and watch Scott's own videos. He's going to be apparently on like everybody's show in the next 6 or 7 days. His lineup. What did you say? You need an agent now?
Yeah, I almost need an agent. Yeah.
So follow him everywhere, but he's mostly on Twitter. And if you follow him on Twitter, that'll probably tell you where he's going to be showing up on various videos. And then Patreon. You're still not on Patreon, huh?
Oh, no, don't worry about it. So I want everyone to save those funds for the real creators out there. Okay, so you don't have to throw any my way. I'm fine. It's just
all right. Okay.
There are other people that deserve it.
All right, Scott, glad to have you on board. And for you and the audience, it's been great talking to you.
Okay, and aloha.
Thank you.